Hello. Today we're going to have a look at some past paper questions about the radiation part of the National 5 Physics course. So let's start with this multiple choice question, and it tells us that the half-life of a radioactive source is 64 years. In 2 hours, 1.44 times 10 to the power of 8 radioactive nuclei in the source decay. What is the activity of the source in becquerels? Pause the video and see if you can work this out. Okay, let's see. Well, if we're trying to work out activity, we're going to use the formula A equals N divided by T, where activity is the number of decays divided by the time in seconds. The fact that the half-life is 64 years is just mentioned in order to tell us that the activity is not decaying, or the activity is not decreasing significantly over the 2 hours that we're dealing with. So the number of decays is 1.44 times 10 to the power of 8. And the time is 2 hours, which we need to convert to seconds. So we do 2 times 60 to get to minutes, times 60 again to get to seconds, which gets us 1.44 times 10 to the power of 8 divided by 7,200, which is 20,000 becquerels, or 2 times 10 to the power of 4 becquerels. Answer A. Question number 2. A sample of tissue has a mass of 0.05 kilograms. The tissue is exposed to radiation and absorbs 0.1 joules of energy in 2 minutes. The absorbed dose is... Pause the video and see if you can figure it out. Okay, so absorbed dose, D equals E divided by M. Absorbed dose is energy in joules divided by the mass in kilograms. So here, our energy is 0.1, our mass in kilograms, 0.05 kilograms, which gives us an absorbed dose of 2 grays. Answer D. The fact that this happened over 2 minutes is irrelevant. It's just extra information given in the question. Number 3. A sample of tissue receives an absorbed dose of 16 micrograys from alpha particles. The radiation weighting factor for alpha particles is 20. The equivalent dose received by the sample is... Pause the video and see if you can work it out. Okay, so the formula for equivalent dose is H equals D times WR, the absorbed dose multiplied by the weighting factor. Here we don't even have to look up the weighting factor, it's given in the question. So 16 micrograys, 16 times 10 to the power minus 6, times 20 is 3.2 times 10 to the power minus 4 sieverts, or 320 microsieverts. Answer E. Question number 4. A sample of tissue is exposed to 15 micrograys of alpha radiation and 20 micrograys of gamma radiation. The total equivalent dose received by the tissue is... Pause the video and see if you can work this out. You will need the datasheet for National 5 Physics. Okay, so to work out equivalent dose, in this question we're going to have to work out the equivalent dose of alpha and gamma separately. So using the formula H equals DWR, and we need to know the weighting factor of alpha and gamma. So we go into our data sheet on the inside cover of the exam and we find out that for alpha, the radiation weighting factor is 20. So 15 micrograys multiplied by 20 gets us 300 microsieverts. For gamma, we can see the weighting factor is 1. So 20 micrograys of gamma times 1 is 20 microsieverts. We add those together and get a total equivalent dose of 300 plus 20, which is 320 microsieverts. Answer B. Question number 5. A sample of tissue receives an equivalent dose rate of 0.4 millisieverts per hour from a source of alpha radiation. The equivalent dose received by the sample in 30 minutes is... Okay, pause the video and think about it. Okay, so we could do this very quickly and see that 30 minutes is half an hour. So if the equivalent dose rate is 0.4 millisieverts per hour, then in half an hour it's going to have accumulated half that much, so 0.2 millisieverts. However, we can use the formula to work this out as well. H dot equals H divided by T. H dot being our equivalent dose rate, H is our equivalent dose, and T is our time in hours in this case. So 0.4 millisieverts, 0.4 times 10 to the power minus 3, equals the equivalent dose divided by 30 minutes converted to hours, which is 0.5 hours. So the equivalent dose is 0.4 times 10 to the power minus 3 times 0.5, which is 0.2 times 10 to the power minus 3 sieverts, or 0.2 millisieverts. Answer A. Question number 6. A radioactive source has an initial activity of 200 kilobecquerels. After 12 days, the activity of the source is 25 kilobecquerels. The half-life of the source is... So, pause the video and see if you can figure this out. Alright, starting at 200 kilobecquerels, we have the activity dropping from 200 to 100 kilobecquerels after one half-life, to 50 kilobecquerels after two half-lives, and 25 kilobecquerels after three half-lives. So in 12 days, three half-lives occur. Therefore, the time for one half-life is 12 days divided by 3, which is 4 days. Answer B. Question number 7, a written question. A technician carries out an experiment using the apparatus shown to determine the half-life of a radioactive source. So we can see we have got a radioactive source placed in front of our Geiger-Müller tube connected to a counter. We have a stop clock in order to measure time, and we've also got a clock on the wall to tell us at what time we're measuring these measurements. So, A. State what is meant by the term half-life. So the definition of half-life is the time taken for the activity of a source to fall to half of its original level. B. The technician displays the data obtained from the experiment in the graph below. So you can see we have a graph of corrected count rate, that's the count rate measured minus the background level, against time. Describe how the apparatus could be used to obtain the experimental data required to produce this graph. So what we need to do is we need to measure the count in a set interval, say over 30 seconds, and calculate the count rate in counts per minute. Then we're going to repeat this every 5 minutes for, say, 35 minutes, as that's the length of time given on the graph. That would give us 7 data points. The last thing we would do in order to get a corrected count rate is remove the source from in front of the Geiger-Müller tube and measure the background count level. We would then subtract that from each of the previous measurements to get the corrected count rate. Part 2. Use the information from the graph to determine the half-life of the radioactive source. So, we can see the corrected count rate begins at 88 counts per minute. So, half of that is 44 counts per minute. How long does it take to get to 44? Well, we can look on the graph and can see that it takes 10 minutes. So the half-life of the source is 10 minutes. Part 3, determine the corrected count rate after 40 minutes. So this is beyond the end of the graph, but we can work out what it's likely to be because we know that it's starting at 88 and every 10 minutes it's going to half. So at 88 counts per minute, that was at the beginning, before any time passed. One half-life, 10 minutes, brought us to 44 counts per minute. Two half-lives, 20 minutes, took us down to 22 counts per minute. Three half-lives, that's 30 minutes, takes us down to 11 counts per minute. Four half-lives, a further 10 minutes, takes us down to 5.5 counts per minute after 40 minutes. So the count rate after 40 minutes is 5.5 counts per minute. Question 8. An airport worker passes suitcases through an X-ray machine. The worker has a mass of 80 kilograms and on a particular day absorbs 7.2 millijoules of energy from the X-ray machine. Part 1. Calculate the absorbed dose received by the worker. So, absorbed dose can be calculated by energy divided by mass. The energy they receive is 7.2 millijoules, that's 7.2 times 10 to the power minus 3, divided by the mass of the man, which was 80 kilograms. And that gives an absorbed dose of 9 times 10 to the power minus 5 grays. Part 2. Calculate the equivalent dose received by the worker. So, H equals D times WR to find equivalent dose. We know the absorbed dose from before, 9 times 10 to the power minus 5. We're also told that it is an X-ray machine that is giving him the dose. So we can look on our data sheet and find the weighting factor for X-rays is 1. So it's 9 times 10 to the power 5, minus 5 rather, times 1, which is 9 times 10 to the power minus 5 sieverts. And finally, part B. X-rays can cause ionization. Explain what is meant by ionization. So, ionization is what happens when an atom loses or gains an electron to become electrically charged. Okay, so that brings us to the end of these past paper questions. I hope you found that useful, and maybe you'd like to move on to the third part of the radiation topic now about nuclear reactions and nuclear power. Until then, I will talk to you again after a while. Bye for now.